Good morning, professors. I'm Liang, and today I'm going to talk about my work on the other P elements in the outer automorphism groups of the extraspecial P groups. First of all, I would like to talk about the background of my study. Gaseous have proved that every finite P group G has a non-inner automorphism of order P or P power. So look at this result. I start thinking about questions. Could I calculate the number of this kind of element? Could I calculate the order P elements? But it is a huge question, because the number of order P elements depends on the type of the groups, the size of the group they're changing. So I start focus on some really specific group called extraspecial P group. Extraspecial P group is a group that the center is equal to the commutative subgroup is equal to the friendly subgroup, and the order of the center is equal to P, and the order of the group is equal to the P to the power of an odd number. Why I consider this group is because it have a great properties that actually the outer automorphism of this group is isomorphic to the symplectic group, which is a subgroup for the general linear group. So this could transfer group theory problems to a linear algebra problem, which much easier to calculate. But let me introduce what is symplectic group. Before I talk about symplectic group, I need to talk about what is symplectic form. Symplectic form is actually a bilinear form to calculate two factors, their oriented area, and actually symplectic group is just a matrix that can preserve this properties like this. You see, if you times the matrix into the factors, it doesn't affect the answers. So it is the symplectic group, the definition of a symplectic group. And after we talk about symplectic group, we now the question is transferred to find the order P elements in the symplectic group. So to find this order P elements in the symplectic group, we need to talk more concept, which is nilpotent and unipotent. Nilpotent is the matrix that to the power k could equal to 0, and unipotent is just the order P elements. But because of the characteristic of the symplectic group is P, so the U could be written as U equal to the I plus N. I is identity function and N is nilpotent. After talk about the nilpotent, I would like to talk about the Jordan normal form. It's just a matrix that formed by a lot of Jordan block along the diagonal, and it is similar to the diagonalizing matrix, so it also could be written at this format, but different from the diagonalizing matrix, it doesn't require the number of the independent eigenfactors is equal to the dimension. It doesn't require. So every matrix could also be written in this format. So I would like to talk about a result from Carter's. This result is really important for my study because he talked about that all the unipoents in the symplectic group is regular, and regular is mean the Jordan normal form, like unipotent is right in this format, and the nilpotent has a Jordan normal form just like this, and the Jordan normal form is just have only one largest Jordan normal block is created by it just have one largest Jordan normal block, and actually the regular. All of the unipotent is regular, and also he proved that the regular unipotent has the same Jordan normal form. So it is really important to my study. But before I talk about how to calculate the number of order P element in the symplectic group, I want to talk about the method. I would like to use the orbit stabilizer theorem. And so when I use this theorem, I need to define what is group action, the orbit, and stabilizer in the group. So I will consider a group action is conjugate. I want to prove that all the conjugates all the unipoents are in the same conjugacy class. The proving is this. It's just the two pair of unipoents, and they, because Carter result, they has a same Jordan normal form, and so you could easily to prove that they are a conjugate. And after this, after this, I proved that all the unipoents are in the same conjugacy class, but I didn't prove that all the conjugacy class has only filled by unipoents. So this is the proof: the unipoent is fill the whole conjugacy class. So after we know the unipoent is fill the whole conjugacy class, we can define a group action just like is like this: from symplectic group times symplectic groups to symplectic group is conjugate. Yeah, and we know the orbit is the conjugacy class, and the conjugacy class is this, but this is not the general linear group. I got a mistake. It's a symplectic group, and Bohr proved that the centralizer, which is a stabilizer of the conjugacy class, is this. The proving of my this proving is not on the paper because I changed it. The original proof is proved by but not in this. This is my proof. And so by the orbit stabilizer theorem, we just need to also the order of the symplectic group is also be given is this. So we just need to define the order of symplectic group to the centralizers, and we would got this is the order of the orbit, and the orbit is the number of the order P elements in the outer automorphism group of the extraspecial P group. And after we got this formula, I want to have a way that to calculate to show the effect that how actually the nilpoents collapse the dimension. So I create this weight, and it is P and you could calculate, because this part S minus I is P to the power P minus 1 is just equal to 0, so it's collapsed all the dimension, and so the dimension of kernel of F would be 2m, and P would be P to the 2m squared, P to the power of 2m. And if we add on all the unipoents to this weight, and you could have this beautiful formula. So this is the end of my presentation. Thank you.